Okay, so I think as I mentioned yesterday, so today I will finish off the part in the equilibrium of beams, which is there are several parts, but what I want to stop, okay, at least we are going to. Uh, so my expectations is we are able to, from this figure, we can develop a observations through the distance as a variable x, and then we could make out the equations both for the shear force, which is this v, and the m, okay, the bending moment. So we have these two expressions in the equations, and perhaps the most challenging part in this topic is to build up these expressions in the graph, and later we are going to learn what is the best way to approach when we have the diagram of the force, and then we are going to transform this diagram into graph of shear force and graph of the moment. There will be some patterns and also some formula that you need to think about it. So basically, from these two expressions, we are going to, so this is so if we slice become two expressions, so the expression one is if we slice, and then we are going to observe the left part, and the expression two, v2 and m2, is the expression on the right side. The difference in the distribution load. So the element one has a distributions of in the rectangle shape, so it has a uniform distribution, and in the right part it has the distributions by the triangular shape. So if you want to write up the equations, so this is the conclusions. So our idea is, so this is going to be, this is the 1, this is 2, so this is v1, v2, this is m1 and m2. Okay, so this is based on the equations that we built on. So if we look at the element 1, the shear force is going to be a linear equation, which is this, which has the 220 as the max, and then it goes down by this negative 40 of with multiply with x, right? So and then it goes by, and then at a certain point it will be crossing this axis, which is at 5.5 feet. So at 5.5 feet, the shear force will shift it to 0, and then it is going to be downhill after the element 1. It's going to be v2. So v2 is this negative 140 plus this, but basically this is a quadratic equations, which is in the upwards positions because it has negative x squared, right? So we have this, which goes to, and also we could see that this is going to be having a maximum, or in this case, the minimum value of negative 140. You could use some basic calculus part to check the coordinates by taking the local max and local mean formulations, which is the first derivative. And you can also check, if we want to check the bending moment, we can check through the first derivative as well. So if we check the bending moment, the second one here, the first one is having a quadratic, which is this quadratic 220x minus 20x squared. So it's a in these positions, and then we have a 140, and basically this is the cubic formulation for the m2. So that's the m2, and we could see this, and we could, for example, we say that we are going to, and they are going to be consistent. So this 5.5, this will be going consistently with this one. Okay, so this is also 5.5. Okay, so this should be going to be consistently, and we know this is going to be maximum, this 5.5, because this is from a positive I think I need to. So let me just. So we can take the maximum from this 5.5, because that is when the v is 0, or in this case here, the gradient, the slope is 0, right? Slope is 0, or if we look from the v1, v2, because v1 and v2 is the derivative of the moment, so we could see that this is changing from positive to negative, which is going to have the local maximum, right? So there will be some calculus here, because you will deal with derivative and integrations, okay? But it will be a simple derivative and simple integrations. So we get this 5.5, and that's why we get the bending moment maximum with this 5.5. We can input this into the bending moment, which is going to be 605. Okay, now is there any way to make up this graphics without sorting out the exact equations, as we can see from this V1, V2, M1, M2? There will be some method, which I will get you into that method for a while. So if we see this, there will be some particular pattern that we can have some conclusions for now. So if we have this load diagram, okay, so you can see the load diagram, and then based on the load diagram, you have the equations, which the left one, that is the equation. So if you see, when you have this kind of a distribution load, then your loads is actually the derivative of the shear force, okay? So you have the distribution load for over the distance x, okay? For over distance x. And basically, when we have this, as we see from the previous triangular shape, we are going to have the quadratic equations, which is going to be, we can see that there will be some smooth curve, okay, that is representing the quadratic equations, okay? And then, similarly, from the moment, we could adjust the curve from the shear force that is going to be a cubic. So if this is technically a quadratic polynomial, then this should be a cubic. Okay, it should be a cubic. So the smoothness, if you see, there will be some sort of differences in the slope. Okay, and then for the concentrated load, so it's not a distribution, the second one, because there is nothing here, then you will see some jump at that point. So the load will be higher here, which then gives you the idea, the shear force here, and then it will be stable, and then jump, and then it's still stable up until this one. Okay, so that's for the concentrated flow. Okay. And then you have another one here. If we have the okay, so the first one is slope. I forgot to explain. So slope of shear diagram, it equals to the value of load. So the load equals to the derivative of the V, the shear force. This third one is we have the change in the shear. so which means the differences, is equal to the integrations, this area, below this area under the curve. Okay. So this will be, I believe it should be very similar to the first one. The differences is the first one, the slope directly our loads, but here we have the change in the V, which is equal to the area. Okay, so it is going to be equal to the area, which is the integration of Px. Okay. And similarly, this will be integrated result from this. Okay. So we integrate this, becomes this, like this one. So we have a constant. We integrate, becomes a linear. And how do we know it's going up or going down? We can see from the graph. Imagine that this line is the axis of 0. Okay. So if it is having a constant force, which is maybe you can decide of going up or going down, right? So if it's going up, which means it's going to be positive. So the constant that is positive will result in the slope that is positive. Okay, for the moment. So basically, moment can be derived or can be developed through the integration of the phi, okay, of the shear force. And then similarly, we have the slope of the moment, which is equal to the value of shear. So this means that the derivative of the moment is v, which is, I think, it will be true for most of the cases. Right? And we see that if we have this equal distributions here, uniform distribution, rectangular shape, then we could see that, oh, we have a V1, and then, as we can also prove from the previous case, it will be a linear equations and then going down through here, V2. And because this is going down, and if this is slope, remember, this means this is in the area of positive. So we can say that this is not this slope, not this slope, but this area is positive. So we can see that this slope is positive. This is positive. This is negative. Okay. I would like to distinguish this one. Okay. I hope you get my point. And then there will be also jump when we have the moment. For example, there is nothing in between, but you have the moment. And this just taking the subtractions of the, because there is nothing there, so we have only the external couple or external moment. So we could get the idea that we could see from we could start from here, taking this moment, and since there is nothing, so we could have a linear, and then going down because it's negative, and then going up again because of the another moment m2, which is, if we take this into derivative, we're going to have a constant shear force, a constant shear force. And then the last one is, if we have change in moment, it will equal to the area under the shear diagram. And this is, again, this is the same as the previous one, which is the rectangular. So we could get this V. Okay. We could get from the linear equations, and then the area. The area of this will be equal to the differences in the m, in the moment. So the m2 minus m1 is equal to the v, and then you could get this is positive area, which results in the slope positive here. Okay. So basically, these two can be related through derivative and integration. Okay. But perhaps this is not really practical. I will show you how to practically using all of this component in a case or study, these 6 points, it could be combined because we don't, like for example, we have this and then we have another triangle here, or maybe we have some concentrated load somewhere and we have some maybe some conditions in each part of the beams, right? Because beams can be in a complexity, right? So let's go for just one example, and I think if we have time, we can have 2 examples, but if not, then one example. So I think this example here. So we have the concentrated load, and this is a simply supported beam. You have the roller pin on the left, and then we have a fixed pin on the right. So perhaps if we would like to imagine maybe we could elaborate the distance first. The answer, I will put the answer over there just to let you know how do we deal with this first. Okay, now because this is both the roller supports and the pin supports, they are going to have a same reactions. So we could have this is going to be, and I think because there is no horizontal forces, I will just write the vertical axis. So this is AY, this is CY. Because if I wrote the CX, it's meaningless, right? Because there's no horizontal forces. So suppose that this is all the forces that is meaningful in our diagram. And then if I describe, because it has length L, so I also can describe this BC as L minus A. Okay, and then as usual, always start with taking the equilibrium for the moment. Okay, so taking for A, for example, and taking this positive. So we could describe this is PA, let me write it like that, and then minus CYL. So P or CY is PA over L. And similarly, if we take the sigma moment of C, we could get the AY and then multiply with L, and then minus P, L minus A. So we get AY is P, L minus A over L. So at least we have the AY, which is P, and then CY. Okay. Now, since we have only the concentrated load, that means the shear force will have a, if we look from this as a starting point, so we will have this load stable, and then at this concentrated load, it will jump, go down. How much? P. And then from here it will be stable, and then we have this this much P A over L. So we can take this, make sure that this is on the same alignment with the picture. Suppose that this is B, point B, and we have the concentrated load, and let's say this is A, B, or maybe B is here, and then C. So first, let me make it about here. Okay. Let me add here. So first is we are taking, this is going to be the axis. And let's name the axis as v of x. And this is the x-axis. So when we start from 0, and then we add a thing maybe here, this will be the p L minus A over L. It will be a constant, stable, up until point B. And then it will goes down up until perhaps this. And how much the distance? The distance should be equal to load P. And we are not expecting any forces, so we only have this C1. So this part here, that this minus this should be equal to this. But since it goes down, we are going to write this as minus P A over L. So this will be up until the P minus PA over L. And then it will be a constant up until this one. Okay, thus this is the diagram. I think the beams should not be included in the picture. I forgot to erase that. So let me erase. It should be only the axis, okay, and the coordinates. So you could determine the area, which is your V. And then from here, we could develop the bending moment. So we are going to write another axis with the same alignment with all the points. So suppose that this is the concentrated load over here. Okay, now how to move from this V to M? So we have positive V. The V is positive here and negative here, which translates that this will be having a slope that is positive and a slope that is negative. Okay? So this will be the M of x. So we can have, this is maybe up until here. And then from here, we are going to have up until this one. We need to make it in the same alignment. So what is this? So what is the maximum diagram here? We could get the PL minus A over L multiplied with A, because that is the A, right? Here, if we start from the left, so the maximum here, the maximum moment that we could describe is basically the moment or the V that we get, P L minus A over L multiplied with A. That's the maximum. Let me write here. Okay, that's the maximum moment. You could write some conclusions by notes, but I don't think you need to write that, okay, unless you are asking to do so. And of course, if you want to make this into equations and the some calculus equations, you could do that. For example, from x equals 0 to x equal a, we could write that the difference in the moment is basically the integration from the vx dx. Or this, the vx, I think I haven't got this vx. Let me write here, the vx is a constant, p l minus a over l for for x equals 0 to x equal a. So we have this vx, a constant. So basically this is just an integrations of a constant, which is basically we just need to multiply with a, which is p l minus a multiplied with a over l. Okay, this is if you need to confirm or to make sure that this is correct. But basically, if you are trained and well-known graphics, you can do the graphics without writing any equations. Okay? The equation is just to confirm, for example, if there is a complexity in the graph, maybe it has like a quadratic function or cubic function that you need to make sure that what will be the maximum bending moment, for example. You need to find this first, and then how to get this, we need to put into the equation and get the number corrected. Okay, so there's some special cases when that's happened. Okay, and if you could see from this, you can see also this is what we have. Okay, actually. So this is the expectations. You could do this graphics observations, and then you could get all the important variable and numbers. Okay, now let me go through. This is if you have the, I will explain this very quick here. If you have the moment, and then if you see the V, there is nothing there, so we have only forces that is based on the reaction forces both sides. Because there's nothing there for the external force, so we have a stable constant V, which results in, because the moment is on the middle or end point B, so we have a certain positive couple moment, and then jump down, and then linearly goes up. And again, this is, you need to make sure that this is in alignment with the diagram. Okay, let me go into a little bit difficult example here. So if we have this, okay, if we have this, so first is we can draw the moment we have the diagram. So this will be, we have reaction force here, AY. We have reaction force here, BY. And because there is nothing on the horizontal, we can basically, for this equilibrium of beams, we can ignore it for a while. So we can concentrate only for the axial force or the vertical force. Okay, so we could see that from here, the loads, if we take with the distance x, from the point AB, this will be -8 kilonewton per meter, or this is going to be dV dx is -8. Which going to be, if we turn this into V, we could see that this is going to be a linear equations. negative 8x, right? So first, we need to take this equilibrium first to find the AY and BY. So take the equilibrium. You can take the equilibrium and basically saying that we are going to have a concentrated load. How much? 32 kilonewton at this 2 meter from the A. So let's say we are going to take this with perspective A, and this will be 32 multiplied by 2, and then minus By multiplied with 4, and then we have the external force 16 kilonewton, so plus 16, and then this will be 6. Complete these equations, we have By equal 40 kilonewton. Same thing with the with B. Let's say B. This is to get the AY. So we have AY with 4 length, and then we have 32 with 2 meter, and then 16 with 2 meter, and we get that the AY should be equal to 8 kilonewton. So you have this is 8 kilonewton, this is 40. Now we could take this 8 kilonewton as our starting point for V. So we could start the V start from 8. Let's say this is 8. And then it will be going down with a slope negative 8. So we get down from this 8 into 40. So 8, and this will be taking some, and what else? So 40, okay, so this will be, so this is expectation. We are going to have something here. Okay. So 8 kilonewton we have the distribution load, which is concentrated into 32 kilonewton. So from this distribution load, we are expecting that this 8 is positive, and then the concentrated load or the distribution load is negative. So we are going to negative with that distribution load from here. We go down minus 32. So minus 32 becomes minus 24, right? So minus 24 is our expectations to get. So let's say here is the minus 24. Let's say this is minus 24. And this is going to be our linear equations. So suppose that this is going to be, okay, our expression for the linear. So this will be negative 24. So this is Vx. And then after that, after we get the negative 32 going down with the distribution load, and then we have By, which is 40. So 40 from negative 24 with plus 40 go up. So plus 40 until 16. So distance here is 16. Maybe 16 is around here. So this will be 16, and then we have a stable, and we are expecting here. So we are going to go up, up. I'm not. It should be straight line with the green. Okay. So this will be, let's say this is 16. up until here. And this 16 kilonewton will be, and you see that we are correct because the 16 is the same as 16 kilonewton on the diagram. Okay. Okay. So when we have this equal, then our graph is correct. Okay. That's how we can confirm. If, for example, this number is not satisfied with the diagram, then there will be something wrong in our graph. Okay. So this is our graph. And this will be the area. For the V. And of course, we could also see that this is having some special distance here. We call this as XM, because this is going to be, when V is equal to 0, then there will be some changes regarding the slope. Okay? And this is very important to see. And the same way, we could generate the bending moment through here. Let me just explain. So from this, we could take the alignment, and then the same thing with here and here. So if you see, this is basically reflections of the moment. It's basically the integration of this part. So it goes down linearly, and then it changes when V is 0, which means the gradient here, the slope here is 0. So it's changed from positive to negative, right? It changed to this positive to negative, which means that there will be some change in this point, which is the, if we compute, this is going to be 1 meter. Okay, this is 1 meter. So this going up, and then maximum going down, and then here is also changed from that part. Okay? So we get that this is going to be go down, and then there will be a stable or a constant from this by here, which is on this negative 32. And then we have another linear contributions from the constant. Okay, this constant is positive, then this is also a positive slope, right? Because this is positive. And of course, we could make the exceptions or perhaps some confirmations through the diagram as this. And basically, from 0 to 4 of the Vx dx, you can compute the area of the triangle, okay, geometrically. Okay, it is the same. So this is net area of triangles. Okay, I think that's it for today. I will upload some additional parts of it, including the some exercises from chapter 4 and this equilibrium. Okay. So next week, Monday, we can have some overview, more practices, and the Tuesday will be our quiz